Okay.
Thank you. Thank you for this wonderful workshop, and thank you for having me here. So I revised my title a little bit to update the field layer to 3 different systems. So we will cover one being the 3D box system, another being this 2D natural field layers, and the third being the 2D moire superlattices. So this work wouldn't be possible without these excellent group members and these wonderful collaborators, as well as the funding agency. So since we have seen a lot of beautiful introductions in the morning session, so I'll just jump into the results directly to save the time. So we will start by this 3D box chrome triodide result. So yeah, as Rolando did, we use Raman spectroscopy to study such a system. We do polarized Raman spectroscopy. For here, we do parallel cross, and then we rotate the incident polarization to be horizontal and then 45-degree rotated. By doing so, we can pin down the Raman tensor and then back out the origin of the Raman modes. After that, we figure out there are a few different kinds. So the first kind is this fully symmetric AG modes that are phonons. Second is this EG phonon modes. And then the third one is the one that Rolando also mentioned, whose Raman tensor is actually anti-symmetric. And because of this anti-symmetry of the Raman tensor, we know it has to be related with magnetism. And we call it M1 and M2 for these 2 modes here, the lower frequency one being 1, the higher frequency one being M2. So the fourth kind is this very low frequency mode that has a energy close to the zone center spin wave gap measured by the neutron scattering experiment by Professor Dai's group. We label them to be M0. So then we do the magnetic field dependence of those modes. We take a look at M0, 1, and 2 first. For M0, we can see that it disperses as the field increases. This tells us that they are indeed spin waves. For M1 and M2, they disappear above a critical field, but then their frequency does not change at all at lower fields when they were present. So then we know that M1 and 2 cannot have spin wave component here because they do not show Zeeman shift. And the third thing is that there is a critical field of 2 Tesla here that we are seeing here. There is a abrupt change of the Raman spectra. And we are dealing with this bulk chrome triodide, whereas this 2 Tesla was originally attributed to the spin flip transition in field layer chrome triodide. So this is one thing that we keep in mind. Then we move to take a better look at this spin wave modes. We fit all the mode frequencies as a function of the field and collapse the data in all channels into this one figure here. What we see here is that below 2 Tesla, we have 3 branches, like 2 of them shift in the opposite direction and a third one just do a linear shift. So this motivates us to propose a model. That is, we have a coexisting state of anti-ferromagnetism and ferromagnetism in this 3D bulk chrome triodide. As to where the anti-ferromagnetism is and where the ferromagnetism is, there are revised sort of like thoughts nowadays for more advanced experiment. Back then, we attribute the anti-ferromagnetism to be at the surface and the ferromagnetism to be in the bulk. Okay, so using this simple model, we can do the spin wave calculation, and then the result mimics our experimental data quite well with a few fitting parameters here. Because we are doing Raman, we cannot have a more complicated model. So we've only considered the nearest neighbor coupling here. Okay, so then we take a look at M1, 2. So for both of them, they onset at about 45 Kelvin, where the layered anti-ferromagnetism would onset in field layers. And they have this 2 Tesla critical field behavior. And further, we consider their frequencies are independent of B field, and they have anti-symmetric Raman tensor form. So then our interpretation here is similar to Rolando's. That is, this M1 and 2 are the magnetism-assisted Raman scattering for the zone boundary phonon. And this zone boundary phonon have exactly the same momentum as the layered anti-ferromagnetism. Okay, so then when the system flips into the ferromagnetic state, we do not have this momentum to assist us to float the zone boundary phonon to the center anymore. So that's why it disappeared. Then we take a look at the more regular phonon modes. We actually see those phonon modes also jumps around this critical field of 2 Tesla. So then it means that they also respond to the magnetic phase transition. And we see that they appear in the originally forbidden channels. This tells us that there is a reduction of the crystallographic symmetry. And here we attribute to a monoclinic crystal structure distortion that happens across the spin flip transition. So that's for our bulk data. We showed the field dependence of 3 different kinds of features. So then we take a look at the 2D natural field layers. And then we look at this so-called layered anti-ferromagnetism assisted Raman scattering mode more carefully in field layers, because here the translational symmetry along C-axis is broken. So since would be more interesting here perhaps. So then we did the measurement for monolayer, bilayer, trilayer, and 4-layer. So one can clearly see that the layer, the mode numbers now increases linearly as the layer numbers. So we have 1 mode in monolayer. We have 4 modes in 4 layers. We label to 1, 2, 3, 4 from high frequency to low frequencies. So this kind of layer dependent frequency behavior can be well explained by the linear chain model while considering the interlayer coupling. So the second thing is that we notice for the parallel channel, we still select the fully symmetric Raman tensors. These are still the regular Raman scattering of the phonons. For the cross channel, they're still corresponding to the fully anti-symmetric Raman tensors. So they are the layered anti-ferromagnetism assisted Raman scattering. And then the third thing we notice is that for the odd layers, we have the very same modes that showing in the parallel and the cross channel. But for the even layers, we have different modes showing in the parallel and cross channels. So then to interpret this, we just have to recall a fact that Raman scattering selects the parity even object. So then we take a look at the parallel channel. So parallel channel are just a regular phonons process. So then they always select the parity even phonons that is listed here. But then for the cross channel, we approximate this procedure to have an intensity that scales with the direct product between the phonon vector and the magnetism vector. So we want this product to be parity even. But then in field layer chrome triodide, the magnetism has alternating parity as the layer numbers increase. So for odd layers, it has even parity for magnetism. So then it will pick even phonons to pair together to produce an even product here. Okay, so that's why for the odd layers, the parallel and cross channel will show the very same sets of the modes. But then for the odd layers, the magnetism is actually odd. So then for this product to be even, it will pick the odd modes. So then that's why for the even layers, the modes are complementary in the 2 channels. So then to test this idea, we can do a field dependence of the 4-layer chrome triodide. So for 4-layer chrome triodide, there are 2 critical fields, one at 0.7, the other at 1.6. So then this will correspond to like 3 types of magnetic structures, okay? And then we have these 4 modes for 4 layers. So their direct product of those vectors are put in this label. Using this label, we can well reproduce the mode intensity changes as a function of the magnetic field when the magnetism switches from 1 to 2 to 3. Okay. So another result in a field layer that we did is that we confirmed that across the field-induced magnetic phase transition, there is indeed a monoclinic structure change. This has been shown in such a way. So we look at the EG phonon mode here. So the EG mode is actually doubly degenerate in monolayer because of the threefold rotational symmetry. But then they are split in bilayer, trilayer, 4-layer due to the interlayer monoclinic coupling. And this frequency splitting is an indication of the monoclinic structure in bilayer and above. And then we take a look at the selection rule here in circular basis. The circular basis shows that these 2 modes, even though they are splitted, but then they primarily only show up in the cross-circular polarized channel and not quite show in the co-circular polarized channel. But once we go across the magnetic phase transition at 0.5 Tesla for the bilayer, we see these two features. The one feature is the frequency split. The frequency actually decreased, whereas the selection rule gets worse, meaning that the symmetry or the Raman tensor's independent tensor element actually increases. Okay, so we attribute to such a cartoon picture here that there is possibly a sliding of the structure between each other, but then simultaneously there is a contraction between layers. So the distance becomes smaller while the lateral registry becomes closer to monohedral perhaps. Yeah. So another thing we want to share in field layer is that we saw a very strong electron-phonon coupling in field layer chrome trioxide. This has been seen as this signature. So this is a wide range Raman spectra taken at field layer chrome trioxide. If we look carefully to this bottom and zoom in here, we can actually see this kind of oscillatory features here. And this oscillatory features goes all the way up to 8 orders. And then we can figure out their intensity, and then we can plot their intensity against the indices of this order, these modes. And then for this kind of intensity versus index plot, we can use Poisson distribution to fit them. After fitting the Poisson distribution, we can get one important parameter, that is the electron-phonon coupling strength for this 2D system. And we can see that this electron-phonon coupling strength actually kicks up and increases by about 50% below this critical temperature of 45 Kelvin. And then we also investigated the field dependence of this property. And we see that this feature or this electron-phonon coupling strength didn't quite change across the spin flip transition in bilayer, while the overall intensity had this jump here. Okay, the last part I want to cover quickly is the Raman measurement for moire superlattices in twisted chrome trioxide system. So we start this twisted double bilayer chrome trioxide. It's a bilayer on top of another bilayer with a twist at the interface of the two bilayers. So in this kind of geometry, we have uniform AFM exchange coupling, interlayer exchange coupling between the top 2 layer and the bottom 2 layer. But we would have a periodically modulating interlayer exchange coupling at the interface of the 2 bilayers. And the reason for us to choose 2 bilayers to stack together is because any homogeneous stacking of the 2 bilayers would give us a 0 total magnetization. This is distinct for stacking monolayer on top of monolayer or trilayer on top of trilayer. So we find this system could be quite interesting to look at. So then our sample is made in the standard way as many other groups, and our twist angle can be characterized by electron diffraction measurement, and the real space superlattice can be visualized by transmission electron microscopy. So again, we use that layered magnetism assist Raman scattering to look at the physics here. So remember before, in bilayer, we only have 1 mode in the cross channel. In 4 layer, we have 2 modes in the cross channel. But here, for this twisted sample at 1.1 degree, we have 3 modes in the cross channel. And again, the selection rule further point to that the cross channel have the anti-symmetric Raman tensors. So then we plot this twist angle dependence of the Raman spectra here with the reference of 4 layer and 2 layers. And we can see that there is a steady trend of the Raman spectra to evolve from more like 4 layer at small twist angles to more like 2 layer at large twist angles. And then the fitting parameters all suggest us that as the twist angle increases, the interlayer coupling, structural coupling is weaker and weaker. So then we further take a look at the magnetic field dependence of these Raman modes. We look at this 1.1 degree first in comparison to 4 layers and 2 layers. For 4 layer and 2 layer cases, they show this very beautiful plateau behavior as we explained before. But then for this 1.1 degree, it shows 2 complicated features that we even don't quite understand now. But then at least we can say 1.1 degree is very different from 4 layer and 2 layer, and it cannot be explained by a simple extension of 4 layer and 2 layers result. So just to show you that for this large twist,
we're actually running out of time. So
I will stop
like
here.
A slide or something, and then you can wrap up. Or?
Just 1 slide to finish. Okay. So yeah. 5 degree is similar to bilayer. 0.5 degree is a superposition of the two. And the final result is that in 1.1 degree, it's so spatial because there is a net magnetization showing up, even though we are stacking two anti-ferromagnets with compensated magnetization. So with that, thank you for your time and attention.
So thanks, Liuyan, for a very nice talk.